Hey everyone, and welcome back to the deep dive.
Yeah.
Today we're going super deep into the world of quantum communication.
Ooh, quantum communication.
It sounds so sci-fi.
It really does, but honestly, it's becoming our reality.
It is.
Yeah, and fast.
Yeah.
It's moving so quickly.
So we're going to be looking at this through an essay.
Okay.
Called Quantum Communication.
Yeah.
Called Quantum Communication.
Percy here.
Übertragung by Jorgo Schneepat,
Okay.
which basically translates to quantum communication. Tap-proof data transmission.
So tap-proof data transmission, that's
It's a big claim.
yeah, it is a big claim, but it's amazing.
It is.
How these principles of quantum mechanics are being used.
Right.
To send information in ways that were once thought to be impossible.
Totally. And the implications are huge. We're talking potentially unhackable communication.
Yeah.
Just because of the laws of physics.
Yeah, just inherent security by the nature of the universe.
Exactly.
Very cool.
So Schneepat really lays out how quantum communication leverages these things.
Okay.
Like entanglement and superposition.
Yeah, those are two big ones.
Okay, so can you break those down for us? Because they're pretty complex topics.
They are. They're very strange concepts, but we can try to make them as simple as possible.
Yeah.
So let's start with entanglement.
Okay.
Imagine two coins, right?
Okay.
And they're linked in a way that no matter how far apart they are, if you flip one, the other one flips to the same side instantly.
Wow.
That's kind of what entanglement is like.
Okay.
These particles are connected in a way that their fates are intertwined, even across vast distances.
It's like magic.
It's like magic. Yeah. Spooky action at a distance is what Einstein called it.
I love that.
So that's entanglement. And then you have superposition, which is a whole other level of mind bending.
Okay.
A regular computer bit, right? It's either a 0 or a 1.
Right, 0 or 1.
Yeah. But a qubit, which is a quantum bit, can be both at the same time.
What?
Yeah, until it's measured.
Okay, so it's like
a spinning coin. You don't know if it's heads or tails until it lands.
Right, okay.
Yeah, and that's kind of what superposition is. Like, this qubit can be in this blurry state of both 0 and 1 at the same time.
Right, okay.
And this is what makes quantum communication so powerful.
Yeah.
And Schneepat does a great job explaining how this works.
So how do we actually use these quantum properties to send information securely?
Right.
How do we go from these mind-blowing concepts to actual applications?
So that's where quantum key distribution, or QKD, comes in.
The CKD.
QKD, yeah, Schneepat describes this as like the flagship application of quantum communication.
Okay, so break that down for us, QKD.
So think of it like this. You and I want to have a private conversation, right?
Yeah.
But we're worried about someone listening in.
Right, always.
QKD lets us create a secret key.
Okay.
That only we know based on the principles of quantum mechanics.
Uh-huh.
And then we use that key to encrypt our conversation.
Okay.
So anyone trying to eavesdrop, they won't have the key and they won't be able to understand what we're saying.
So it's not about sending the message itself through a quantum channel.
Exactly.
It's about sending the key.
It's about secure key exchange.
Gotcha.
Yeah. And the best part is, any attempt to intercept this key exchange is immediately detectable.
Wait, really?
So Schneepat explains one way of doing this, using the polarization of photons.
Okay.
So think of it as whether they vibrate horizontally, vertically, or diagonally.
Okay.
And we can encode information in that.
Okay.
Now, any attempt to measure these photons, to spy on the key, alters their state.
Oh, wow.
It's like setting off an alarm.
So it's like the act of eavesdropping ruins the information.
Exactly. You can't just peek at this information without changing it.
That's amazing.
It is.
So there are multiple ways to do this.
Schneepat describes a bunch of QKD protocols, each with its own unique approach.
Okay.
Like BB84.
Okay.
And E91.
Okay.
BB84 uses the polarization of photons, like we just talked about.
Yeah.
E91 uses entangled pairs of photons to achieve the same goal.
Okay, so they all take advantage of quantum mechanics.
They all do.
To ensure that the key exchange is secure.
Exactly. It's not about building higher walls. It's about changing the rules of the game altogether.
Wow.
Yeah.
Okay, hold on, because this next concept might just blow our minds.
Yeah. Okay.
Quantum teleportation.
Quantum teleportation. Yeah, Schneepat describes this, but before you jump to any Star Trek conclusions, we're not beaming people up.
Okay, good.
Not yet. Anyway.
Not yet.
So quantum teleportation is about transferring the state of a qubit.
Okay.
Not physically moving the particle itself.
Okay.
It's more like sending a blueprint for building a perfect replica.
Okay.
Than sending the actual object.
Gotcha.
Yeah.
Okay, so walk us through it. How does that work?
So it starts with an entangled pair of particles.
Okay.
You take one of them and you combine it with the qubit you want to teleport.
Right.
And then you measure both of them.
Okay.
You send the results of that measurement, which is just ordinary information. to the destination.
Yeah.
And because of the entanglement, the recipient can use that information to reconstruct a perfect replica of the original qubit state.
Okay, so you're sending information about the qubit, not the qubit itself.
Exactly.
That's pretty mind-blowing.
It is. It's very strange.
But wait, what happens to the original qubit during all of this?
It gets destroyed.
Oh.
Yeah, it's like sending a message written in disappearing ink.
Oh, wow.
This destruction is crucial because it upholds something called the no-cloning theorem.
Okay.
Which basically says you can't simply copy an unknown quantum state.
So it's like a one-time transfer.
It is.
Which makes it even more secure.
Exactly.
Okay.
And what's even more fascinating is this isn't just a theoretical concept. It's been experimentally demonstrated with photons.
Oh, wow.
Which opens up incredible possibilities.
So it's actually real.
It's a real phenomenon that scientists are working with today.
Wow.
And it's just one example of how quantum mechanics is changing the world around us.
This is all so fascinating.
It is.
But we've only just begun to explore this quantum rabbit hole, haven't we?
We've only just scratched the surface. There's so much more to discover.
What else does Schneppad have in store for us?
Well, next we'll tackle the challenge of sending quantum information over long distances.
Okay.
And explore how scientists are working to build a global quantum internet.
A quantum internet?
Yeah, stay tuned.
I can't wait. Welcome back to the deep dive.
Yeah.
Last time we were talking about entanglement, superposition,
quantum teleportation.
It's incredible, all these concepts
I know
that are being used to create these ultra-secure communication systems.
Yeah.
But like with any powerful technology,
yeah,
we need to consider the challenges.
Yeah, absolutely.
Yeah.
Schnepphat points out that one of the biggest hurdles is sending quantum information over long distances.
Right, because like even with our regular internet,
exactly,
we have problems with that.
All the time.
Yeah, the signal weakens.
Yeah, you get that buffering.
Yeah, exactly.
And in the quantum world, it's even worse.
Oh, really?
Yeah, because quantum information is very fragile.
Oh, okay.
So maintaining that over long distances, that's a major obstacle.
So how do we solve that?
Yeah.
Is there like a quantum version of a Wi-Fi extender?
Kind of, yeah.
Okay.
Schnepphat introduces this concept of quantum repeaters.
Quantum repeaters.
Yeah. And these act like relay stations.
Oh, okay.
They extend the reach of entanglement across long distances.
So they're like
secure communication hubs placed along a network.
Right.
To make sure that the quantum information remains intact.
Gotcha.
Even as it travels thousands of kilometers.
So it's like a chain of trusted messengers.
Exactly.
Carefully passing along this secret message.
Yeah.
Without altering it.
A very delicate handoff.
Yeah. That's amazing.
Yeah, that's pretty cool.
But how do these quantum repeaters actually work?
Right.
Are they using tiny quantum robots or something?
Not quite robots, but the idea is kind of similar. Schnepphat explains this really mind-boggling concept called entanglement swapping.
Entanglement swapping.
Yeah, so imagine you have two pairs of entangled particles separated by a large distance.
Yeah.
Quantum repeaters can be used to link these pre-entangled pairs, effectively bridging the gap between them. It's kind of like connecting two short ropes to make one long rope.
Right.
Except we're doing it with entanglement instead of rope.
Oh, that's interesting. So we're not teleporting the information itself.
Right.
We're just extending the entanglement across the distance.
Exactly.
That's pretty clever.
It is. It's a very clever way to get around this distance problem.
Yeah.
And this leads us to the grand vision that Schnepphat outlines.
Wow.
A global quantum internet.
A quantum internet.
Yeah.
Whoa.
Imagine a network where quantum computers and other quantum devices are all interconnected, enabling secure communication and computation on a scale that we can only dream of today.
So hold on, a quantum internet. Are we talking like sending cat videos at the speed of light or something?
Haha, not exactly.
Right.
While the potential applications are still being explored,
yeah,
secure communication is a big one.
Right.
Imagine being able to send like sensitive diplomatic messages
right,
or conduct high-stakes financial transactions
right,
with the absolute certainty that no one, not even a quantum computer-wielding supervillain, could eavesdrop.
That would be game-changing.
It would be, yeah.
So what else could this quantum internet do?
Schnepphat also mentions distributed quantum computing.
Distributed quantum computing.
Yeah.
Okay.
So imagine multiple quantum computers linked by these secure quantum channels working together to tackle problems that are currently impossible for even the most powerful classical computers to solve.
So it's like creating a giant quantum brain.
Yeah.
With each computer acting as a different region.
Yeah. working in parallel.
All working together seamlessly. The possibilities are mind-boggling.
They are. It's really exciting. And it's not just theoretical.
Yeah.
Schneppat highlights some real-world projects that are paving the way for this quantum future.
Oh, wow. Like what?
The Chinese network, for example, already spans over 4,600 kilometers.
Wow.
And they've even launched the MESHA satellite, which is the world's first quantum communications satellite.
So this isn't just some distant sci-fi dream.
No.
It's actually happening now.
It's happening right now.
Wow. Are there any other projects going on around the world?
Definitely. Schneppat mentions that the EU is also heavily invested in quantum networking, with ambitious projects like EuroQCI and the Quantum Internet Alliance.
So there's a global race to build this quantum future.
Absolutely. It's a very exciting time to be working in this field.
It's incredible how quickly this field is advancing.
Yeah.
But I'm curious.
Yeah.
With all this talk about quantum computers and the potential threat they pose to current encryption methods, isn't there a risk that this quantum internet could become like a double-edged sword?
That's a great question, and it brings us to a really crucial point that Schneppat emphasizes. One of the biggest drivers of quantum communication research is security. Because as quantum computers become more powerful, a lot of our current encryption methods, like RSA, they become vulnerable. It's like facing a new breed of super spy, equipped with tools that can crack our best codes.
So it's a race against time.
It is.
We need to develop quantum-safe communication before quantum computers can be used to break our existing encryption.
Exactly. We need to stay one step ahead. And that's where quantum communication comes in. It's like building a fortress of security that can withstand any technological advancements, ensuring that our data remains private and protected now and in the future.
This is all incredibly fascinating.
It is.
But I have to admit, it's also a little overwhelming.
I understand it's a lot to take in.
Yeah, it feels like we're on the verge of a technological revolution that could fundamentally change the world as we know it.
It's true.
Where do we even begin to process all of this?
It's a journey of discovery. We're all in this together. Schneppat has provided us with this incredible roadmap. And by understanding these basic principles and the challenges involved, we can start to grasp the magnitude of what's happening and participate in shaping this quantum future.
That's a great point. So as we continue exploring this quantum rabbit hole, where do we go from here?
Well, next we'll step back and look at the bigger picture. What are the implications of a world with ultra-secure quantum communication? And how will this technology impact our lives in the years to come?
Interesting.
Stay tuned.
Welcome back to the deep dive. It's crazy how far we've come.
I know, right?
From these weird concepts of entanglement and superposition. To a real possibility. Of like a global quantum internet.
It's pretty mind-blowing.
It is. And we've been exploring all this. Through Jorgo Schneppat. And his essay on quantum communication.
It's been a really interesting deep dive.
It has. What really stood out to me was this like fundamental shift. In how we even think about security. Schneppat really emphasized that with quantum communication, we're not just trying to build higher walls. We're like changing the rules of the game.
Exactly. We're not just trying to make it harder to break in. We're making it impossible. By using the laws of physics.
And it's not just about protecting data. It's about creating a more trustworthy and resilient digital infrastructure for everyone.
Absolutely.
But I think with all these advancements, it's important to remember that technology is a tool. And like any tool, it could be used for good or for bad.
It's a double-edged sword.
Exactly.
Schneppat doesn't really dive deep into the ethical considerations. But it's something we need to be mindful of. As we embrace this quantum future, we need to make sure we're building it on a foundation of ethical principles.
Are we thinking about who has access?
Exactly.
How is it governed?
What are the unintended consequences? We need to ask those hard questions.
It's easy to get caught up
absolutely.
in all the exciting possibilities without really thinking about
the potential downsides.
It's kind of like the early days of the internet.
Exactly.
Like no one could have predicted how it would transform society.
For better or for worse.
For better or for worse, exactly.
And I think quantum communication has that same potential to be just as transformative. But we have the opportunity to learn from the past,
right,
and shape this new technology in a way that benefits everyone.
Absolutely. It's going to require open dialogue,
yeah,
collaboration,
definitely,
commitment to using this technology responsibly.
Couldn't agree more.
We need to make sure that the quantum future is one that we can all be proud of.
All said.
So as we wrap up this deep dive, I want to thank you for joining us on this exploration of quantum communication.
The pleasure's all mine.
With Yurgo Schneppat as our guide.
He gave us a lot to think about.
He really laid it all out for us.
Yeah.
Hopefully you're walking away with a better understanding of this incredible technology.
Yeah.
And its implications for the future.
Absolutely.
And remember, even though this deep dive is over,
the
exploration continues.
It does.
We encourage you to learn more about quantum communication. Ask questions.
Yeah, stay
Engage in the conversation.
Absolutely.
The future is being shaped right now, and we all have a role to play.
We do.
So until next time, keep diving deep.
And keep exploring.
See you later.